All right. Welcome back. This is our second day of chemical reactions. The first day we went over some CK12s. The second day we went over some vocabulary lessons, introducing it to you guys. But today we're going to go deeper into our notes. So make sure that you're taking your notes. Take everything that you see written down on the screen so that you can get all of your credit for today's assignment of notes and starting with chemical reaction. We're going to start with a video of a whole bunch of really cool chemical reactions. So let's check them out. Turn up the volume so you guys can hear it, and we'll give it a go. All right, so those are all different chemical reactions. If I were to tell you that I knew every single one of those and could do every single one of those before I saw that video, I'd be lying to you. But they're pretty cool, so I figured I'd give you an opportunity to check those out. and see a little bit what we're talking about before we dive into it a little even more deep than we have already. So let's talk about reactants and products. Reactants are the substances that we start with our chemical reactions. So those are what we're given. That's where we start. So in a lot of those cases, it would be before the fire was added, before the soap and the milk was added to the colors, and so on and so forth. So you see, that's what we start with, and the products are end result. So you saw all those cool things like growing, or when that tablet was dropped into the water and there was like a pink little explosion that occurred. Those are our products. That's what we're getting back from the reactants. When the bonds in the reactants break and the products form new bonds to create new things. Something that we've all heard about since we were little kids, probably about 4th grade science, we started talking about photosynthesis. Well, photosynthesis is just a chemical reaction that occurs when you input carbon dioxide, sunlight, and water. You get out from the sunlight, carbon dioxide, and water, you get out oxygen and sugars. So that is what photosynthesis does. So our products in photosynthesis are oxygen and sugars. That's what we're getting out. That's what we get from the plants. And what we're putting in the reactants are the light, water, and carbon dioxide. So we started with light, water, carbon dioxide, and those are our reactants. We end with oxygen and sugar. So you can see that here in this picture. You see the sun on the left side, you see the carbon dioxide little molecules flying in, and then the water coming up from the roots. Those are our reactants. And then on the right, like on the left side, we still see that bigger picture, not the cell portion, but you see oxygen coming out of the leaves and sugars coming out of the leaves. So those are our products and reactants and products. So let's talk about the 5 types of chemical reactions. And instead of Mr. Moore's voice talking about them on repeat and telling you more and more about them, we're going to let this lady give you kind of a quick overview of what these 5 things are before we talk about them again.
Take a deep breath. We'll identify the different types of chemical reactions together. Hello everyone, I'm Melissa Maribel, your personal tutor, and the first type of chemical reaction is known as synthesis or combination. Here's an example. In a synthesis reaction, 2 different reactants combine to form our product. Note, the reason why hydrogen and chlorine have a 2 subscript is because they are known as being diatomic molecules. Diatomic molecules are atoms that exist in pairs. Here is a list of diatomic molecules. Now, if we flip this synthesis reaction, you'll see it's now a decomposition reaction. Because in a decomposition reaction, you have one reactant that is being broken apart into multiple products. The next reaction is a single replacement or a single displacement reaction. Here's an example. Our reactants are 1 element plus 1 compound, and those form 1 element plus another compound. Notice that we are just switching the metals to form our new products. A double replacement or double displacement reaction is really similar to this, because our reactants are now 2 compounds and those form 2 different compounds. Think of it this way. The inner elements combine and the outer elements combine to form our new products. Or you can think of it as the metals are switching again to form our new products. Up next is a combustion reaction, which occurs when something is burning. This is the general equation. And here's our example, where our first reactant consists of only carbon and hydrogen. Or we can have our first reactant consisting of carbon, hydrogen, and oxygen. Your biggest clue that something is a combustion reaction is that the second reactant is O2, and our products are carbon dioxide and water. These never, ever change. Now, in an acid-base neutralization reaction, we have an acid plus.
All right, we're going to stop right there because the 5 types we're talking about, she talked about right off the bat. We're not going to talk about neutralizing acids and bases. That's not something we'll have a lot of discussion here in this class. That might be something you talk about in a higher level chemistry class, but we're going to keep it to the most basic, simple 5 types of chemical reactions that we're going to be discussing in class. She did a great job explaining them, so let's go a little bit deeper. So, synthesis reaction. Remember when we went through the CK12, Mr. Moore told you it's where 2 or more reactants combine to form a single product. This was like when Mr. Moore was like, hey, this is like when Mr. Moore and Miss Wood were 2 entities, and then they got married and became one. So it was Mr. Moore and Mrs. Wood as one, as opposed to 2 separate lives. Now we bring our lives together as one. Same concept here. This is what we're talking about. We have reactants that combine to form a single product. So the one that we have been talking about since we started talking about ions and cations and anions and bonding, chemical bonding, is sodium and chlorine to create sodium chloride, which is our table salt. So that is a synthesis reaction. We have sodium, we have chlorine. They come together to make sodium chloride, and we get table salt, which is delicious to put on French fries. Just saying. Side note. Sidebar. All right, decomposition reactions. Just as the lady said, it's where we have one reactant, it breaks down into 2 or more products. So we have these pictures right here. We have water breaking back down into our 2 products, which are O2, oxygen, or H2, hydrogen. Now, most of the time, decomposition reactions do take an outside energy force, but that's something we won't talk much about. But let's listen to this video for just a few seconds. We're not going to even really listen to it. We're just going to look at it, look at the picture that pops up initially, and then move forward because it's a 5-minute video that we don't need to watch. But decomposition reactions.
Decomposition reactions. Now,
decomposition reactions are the opposite of synthesis reactions. That's what you need to remember. Synthesis brings together, decomposition breaks apart. Okay? So where we would bring oxygen and hydrogen together to make water, we break apart water to make hydrogen and oxygen separate as gases. Okay? So they're just the opposite. That's what we're looking at here. So let's go ahead and jump to single replacement reactions. Single replacement reactions, when I think about single replacement reactions, I think about Mr. Steal Your Girl or Mrs. Steal Your Man's. All right, that's where one element replaces another element in a single compound. That would be like if you and your best friend were hanging out and your best friend had a girlfriend and you were like, man, I really like that girl. I think she's awesome. And she looked at you and was like, oh, I really like him. And so she leaves your best man's, your best friend, girl or boy, and comes to date you, whatever that significant other is. You have now replaced them. So we see this as A plus B, or A plus BC becomes, now B is single for best friend, plus AC, because now A and C are together instead of B and C being together. So let's see what this looks like in our chemical equation. So typically we have an element by itself, which is K. K here steals OH from hydrogen. So instead of being water still, it becomes KOH plus hydrogen gas, or H2. So it stole the oxygen and a hydrogen and 2 hydrogens from the water molecule to make hydrogen now a gas and create an entirely new compound, which is our K2KOH, which is potassium, oxygen, water, or hydrogen. Potassium, oxygen, and hydrogen. All right? So that's like a single replacement. The K was by itself on the reactant side. And then on the product side, the K had a partner. So let's look at double replacement reactions. This is like you and your best friend are dating people, but then you're like, I like your significant other more than I like mine. And your best friend's like, man, I like your significant other than I like mine. Let's switch. So they switch partners. Two ionic compounds exchange ions to create new ions. So that's like A and B being together, like you and your girlfriend, plus C and D, your best friend and their girlfriend or boyfriend, significant other, whatever. And then those people switch places. So A and D are together now instead of C and D. And A and B or C and B are together instead of A and B. All right. Now I know that that's a silly thing. Obviously, I hope that doesn't happen. That's a sad day. But I just am using it as an example to kind of show you what this looks like. NaCl are hanging out, and then with AgF. Well, Cl leaves Na to go to Ag, and F leaves Ag to go to Na. You see how the F and the Cl switched spots and had a different partner on the product side of our chemical reaction. The reactants started one way, and they switched partners on the product side of our reaction. That is a double replacement. Now the combustion reaction, which is our final reaction that we talk about when it comes to types of chemical reactions, is one of the most common that you would see in like an action movie. These are our explosions. These are our things where we're going to have basically some kind of, it doesn't always have to be violent, but you think about a car engine, that's called a combustion engine, and what happens is there's a reaction, chemical reaction that occurs between the gas and the fire in there that creates the motion and the energy that you need to be able to drive your car forward, or your parents to drive their car forward. And this is when a substance quickly reacts. So it's quick to react with oxygen. So oxygen is always going to be involved in a combustion reaction. The products will also always include carbon dioxide and water. So if you ever look at your parents' tailpipe after they have driven, you're going to see carbon dioxide will come out, but also sometimes the tailpipe drips water because the combustion reaction is producing carbon dioxide and water. So these things are like fire and stove. And we're going to watch a quick combustion reaction right here.
皆様どうぞカウントダウンご唱和ください。もう間もなくでございます。さあ、それではカウントダウン参りましょう。10、9、8、7、6、5、4、3、2、1、どうぞ。どうぞ。でございます。もう間もなく素晴らしい花火をご覧いただきますので、どうぞカメラをお持ちの皆様ご準備くださいね。
So you see how fast that chemical reaction occurred. It was almost instantaneous. Now, of course, there was a countdown. There were some things that happened. But once the wick was burnt out, there was an explosion that occurred the moment that the fire and the oxygen and the gas or whatever was inside of that fire, gunpowder, whatever it might have been, inside of that firework that exploded, and it exploded violently and quickly, which is how most combustion reactions work. Now, can we control combustion reactions? You should already know the answer to that. The answer to that is yes. Yes, we can. And we have, by having cars and motorcycles, things of that nature, having engines that run on gas. So let's look at something that is important to need to know, because if you're watching all of these other chemical reactions and hearing about these other chemical reactions, the only time you really ever heard anything about energy was when we talked about combustion reactions. Well, the truth is all chemical reactions require energy. So energy in reactions, like I just said, they either need energy to come in and be a part of what they're doing to be able to react, or they put energy out. So they're either going to be like our combustion reaction, where it obviously put energy out in the form of light and heat, or they're going to take energy in, which then takes energy in the form of light and heat away from the environment around them. And we'll talk about a little bit of those as we go forward. So like I said, energy is needed in all chemical reactions. There are two types of energy: exothermic and endothermic. So we're going to talk about those two after this short video. Oh, I forgot. Pictures first and then the video. So this picture is of a guy being cold. This picture is of temperature rising and light in it. So those will make a little bit more sense, but one of them represents endothermic and one of them represents exothermic. I think you might already know the answer to which one represents which, but we'll go ahead and move forward in this video and watch this video. But for 5 points extra credit, the first person that comes up to me and correctly tells me which picture represents endothermic will get 5 points extra credits. First person in each class. So let's watch this video now.
You know how sometimes you go to bake a cake, but your bananas have all gone rotten, your utensils have rusted, you trip and pour all of your baking soda into the vinegar jug, and then your oven explodes? My friend, you and your chemical reactions have fallen victim to enthalpy and entropy, and boy are they forces to be reckoned with. Now your reactants are all products. So what are these E words, and what's their big idea? Let's start with enthalpy, an increase or decrease of energy during a chemical reaction. Every molecule has a certain amount of chemical potential energy stored within the bonds between its atoms. Chemicals with more energy are less stable, and thus more likely to react. Let's visualize the energy flow in a reaction, the combustion of hydrogen and oxygen, by playing a round of crazy golf. Our goal is to get a ball, the reactant, up a small rise, and down the other, much steeper slope. Where the hill goes up, we need to add energy to the ball, and where it goes down, the ball releases energy into its surroundings. The whole represents the product, or result of the reaction. When the reaction period ends, the ball is inside the hole, and we have our product, water. This, like when our oven exploded, is an exothermic reaction, meaning that the chemical's final energy is less than its starting energy, and the difference has been added to the surrounding environment as light and heat. We can also play out the opposite type of reaction, an endothermic reaction, where the final energy is greater than the starting energy. That's what we were trying to achieve by baking our cake. The added heat from the oven would change the chemical structure of the proteins in the eggs and various compounds in the butter. So that's enthalpy. As you might suspect, exothermic reactions are more likely to happen than endothermic ones, because they require less energy to occur. But there's another independent factor that can make reactions happen: entropy. Entropy measures a chemical's randomness. Here's an enormous pyramid of golf balls. Its ordered structure.
All right, we're going to stop right there because we're not going to get into entropy. But that is how chemical reactions work. All chemical reactions have energy. Now, like he said in the video, it's easier to have an exothermic reaction than it is to have an endothermic reaction, because most of the times with endothermic reactions, there has to be an outside source putting energy in to be able to have that functionality of that reaction. So let's talk about them specifically. Exothermic reaction is like an explosion. I couldn't have timed that better if I tried, and I didn't try, which was actually pretty good. But it was like an explosion, right? And so the more energy to form new bonds in a product. So it takes more energy to form these new bonds than it did to break the old bonds. These release energy in the form of light or heat. And what I mean by that is taking more energy that because it used more energy at the beginning, we bond these new products together and we have all this leftover energy. And just like matter, energy can't be created nor destroyed, so it has to go somewhere. It comes in the form of heat or in the form of light. And so it releases that energy back out into the environment, like that firework or that explosion we just saw. That energy, the new bonds that were created, then it let go of the excess energy that they did not need anymore, and it became light or firework. So all combustion reactions are exothermic. Every single one of them. There's not one combustion reaction that is endothermic, all right? So leading up to endothermic, let's talk about it. What is the difference? Endothermic reactions, well, they take more energy to break the bonds in the reactants, right? Well, while it took more energy to create the bonds in the products than it did in the reactants, more energy to break the bonds. So to get this thing started, it's got to pull energy from the environment around. Well, it can do this in so many different ways. In the video that we're about to watch, actually, it pulls energy from its natural environment. It doesn't have to have anything added to it. Like the cake we saw in the video needed heat added to it by an oven. This video will show us that it can do it without. But we see things like ice packs. When we break them up, we add energy by breaking them up with our hands. That puts energy into the ice pack to create the chemical bonds breaking and creating a new feeling. And that's why ice packs, when you initially touch them, aren't cold, but then you can break them up and they cool down really fast. And then photosynthesis. We use light from the sun. The plants use light from the sun to get the reaction started from water and carbon dioxide to create those sugars. So here is an endothermic reaction.
What I have is some barium hydroxide. Okay, and I'm going to put this into the. In fact, you know what? I'm going to do this in one of the beakers, not that thing, because it's ridiculous. Barium hydroxide, and I've got some ammonium chloride. Now, what I'm going to do is mix these together, and hopefully we should see a endothermic reaction. Yes.
It's with the hand stuff.
What hand stuff?
The hand sanitizer.
Oh, it just lives on my desk.
Oh.
I was chopping up hearts earlier, and yeah, I need to be not covered in blood. So, what I'm going to do to show how exothermic this is, how much heat this is taking in, I'm going to make this wooden block wet. Okay? Now, you will see why I've done that in a second.
Sweet.
So, I'm going to mix these two things together and carefully. I need to break that up a bit. Mix these two things together. Well, hopefully not, because if it's blowing up and giving out huge amounts of energy like that, that would be what type of reaction? Exothermic. Now, we want to see endothermic, so it's going to be a little bit more subtle. So, I mix the barium hydroxide and the ammonium chloride together,
Does it freeze?
and they should start to react.
Does it freeze it?
Well, we should soon see. So they're mixing together. Now, can you see how the consistency of that is changing slightly? It's sort of clumping together, because one of the products it's making is water in this reaction. And you can see actually that's all gone liquid, and it was all just solid powders. It's not milk. You wouldn't want to milk it.
Oh.
Okay, if you put that in coffee, there'll be problems. Now, one of the products of this, because it's ammonium chloride, is it's giving off ammonia, which smells rather horrible. And I'd forgotten about that, which is why I just breathed the huge load in. That sort of horrible, slightly tangy smell in wee is sort of ammonia-like.
Oh, is that what I can smell?
Yeah, that's what you can smell. Unless you've wet yourself, that is the best way you can smell. Okay, but also, actually, this is getting actually very cold as it's going along. Okay, now hopefully, if this has worked, it's getting cold enough. Well, you know, I put water on the base there.
Yeah.
Fingers crossed. It's actually frozen the water onto the bottom. Now, this reaction has worked so well, so much energy has had to be taken out of the environment. It's got that water so cold that it's dropped below freezing and frozen onto the bottom.
How cold?
That is pretty cool.
How cold is it?
Well, I haven't got. In fact, I have got.
So that's how endothermic reactions work. They take energy from the world, the environment around them to make them happen. So as you saw in that product, it took so much energy from the water that it slowed down the molecules to a point where they became actually close together, which we talked about. Remember, solids, liquids, and gases, and plasmas, but we're talking about liquid to solid here. they slowed down so much that they got so tightly packed close together that they quit moving so fast that they were a liquid and began to freeze, and they became a solid, which then that solid attached that beaker to that wood block. That's the kind of thing that we're seeing with endothermic reaction. Well, this is the end of your notes for today, so go ahead and make sure that you are getting these notes finish writing them out, and get them shown to me so that I can give you a grade and go ahead and move forward to your next assignment for today.